Hello everyone. We will continue our discussion on the chapter 4. So in this lecture we are going to talk about examples of Fraunhofer diffraction patterns. And as a first example we are going to talk about rectangular aperture. So rectangular aperture with an amplitude transmission given by TA xc eta is given by this one. Once again, we are going to use xc as the horizontal axis in the aperture plane and eta as a vertical axis in the aperture plane. So in this case, we have in horizontal axis, we have a wx minus wx, and we have a wy minus wy. So we have this kind of a rectangular aperture. So this is what we are going to have. And of course, other than this inside region, everything is black. So that means there's no light. And if the aperture is illuminated by the unit amplitude, normally incident monochromatic plane wave. So we are going to assume that we have a plane wave coming into this aperture plane. Okay. And then what we are going to do is that in the case of a Fraunhofer diffractions, we know that Fraunhofer diffraction field is going to be Fourier transform of field at the aperture plane. Okay, and then you Fourier transform those intensity field. And then you utilize this substitution. This is very important. So here the special frequency is given by x over lambda z, and the special frequency y is given by y over lambda z. So in the here in the somewhere in the observation plane, we are looking at the spatial distributions. And then this is what we get in the real space, but it is actually the Fourier transform given by this relationship fx and fy, but it is actually spatial position. Okay. So if you do the Fourier transformation, so rectangular function becomes a sinc function. So for the case of xc eta, we have a sinc function on xc and the rectangular function on the xc axis and rectangular function on the eta axis, and then we get this relationship. Okay, and then once again we are going to replace fx and fy into x over lambda z, y over lambda z. Okay, and this is what we get. This is what we have in the observation plane. Everything is given in terms of x, y, and z. And then intensity is, of course, is given by u star. Okay. And then you have a magnitude, then this exponential terms is gone away. And then a square over lambda square g square, and then sinc square. Okay. And then this is going to have a look at it. So if we normalize this one on the horizontal axis, we have this kind of sinc functions. Remember the sinc function is sine x over x so that it should have this going plus and minus, but we have done the sinc square so that it is all positive. Remember that this is our intensity, okay? sinc square x. Okay, and this is what we get. So along the x directions we have a sinc, and along the y direction we have also sinc. Okay, and then the dose period is given by this one. Okay, this period is given by these functions. Okay, now let's move on to circular aperture. Circular aperture. So in the Cauchy-eta plane, once again, the aperture plane, we have circle. And then we call it circle function. Okay, so inside of this radius, and then we have the 1, but outside is 0. But because of this cylindrical symmetry, once again, we are using cylindrical coordinate, which is kind of a Q here. Actually, it is, yeah, I don't know why they are using it, but we are following the text. And then if R is the radius coordinate in the observation plane, we have x, y. So in this case, we have a R, and we have a Q, okay? And then Fourier transformation in the cylindrical coordinate system becomes a Fourier vessel. Fourier vessel. And those who don't recall this, you need to go to chapter 2.15. The Fourier transform in cylindrical coordinate becomes a Fourier vessel transformation, such that we use the B instead of F in cylindrical. But anyhow, what we are going to do is that doing the Fourier transformation. There's no change of it, but you need to look at this one once again. In the special case, the low is the kind of a spatial frequency in cylindrical coordinate. So it is matching with Q, and this is the coordinate in little space. And then note that Q is given by Cauchy square plus eta square square root, and similarly, rho is given by fx square plus fy square, the radius in the spatial frequency domain. Okay. And then for the case, it is also important to note that normally incident plane wave, unit amplitude, and then this becomes our actual the field transmitted by the aperture is equal to the amplitude transmittance. This becomes our U, Cauchy eta, okay? And then our Fourier vessel transformation of a circle is given by this one. And then the amplitude distribution in the Fraunhofer diffraction pattern is given by this one. Okay. Note that J1 is the Bessel function of the first kind, and then is very, very similar to sine over x. But in the case of a cylindrical coordinate, sine can be replaced by the Bessel function of first kind 1, and then this is the low. Okay, and then as a result, the intensity distribution is given by, once again, use the U, and then it shows this distribution, and we call it usually is an Airy pattern. Okay, this is what we get. So if you go back to general physics, and then there is a circular aperture, and this is what you get at the screen, and this is what you get. Okay, so it took a long time to mathematically show what it is. Okay. Okay. And now, as a third example, we are going to talk about a sinusoidal amplitude aperture. So that it looks like a kind of it's a transmittance is 1. Outside this aperture, we have a rectangular form. And then within the rectangular, we have this kind of modulation along horizontal axis. Okay. So we have a rectangular aperture, and then on the top of it, we have this kind of modulation like this. Okay. So actually, this is the horizontal axis. And then as m gets to 1, then we have a full modulation. And then if m is small, then it is a slight modulation. Okay. So that means we have a kind of a rectangular aperture. And then it shows like, and within this we have this kind of a distribution along C, and within the along the eta direction, it is everything is same. So it shows. Okay. And then we need to find out the Fraunhofer diffraction pattern, and then we do the Fourier transformation. And then we get the Fourier transformation of this part. Modulation part is given by this one. And then we have a Fourier transformation of this part is, as you know, we have this sinc function. And then what we do know is that convolution theorem can be used to write each of them. And then we have, if you do the Fourier transformation of, if you know the convolution in the Fourier domain is just a multiplication. And then we eventually get this kind of functions. So we have a sinc function, and then multiplied by another sinc function, and then shifted by these functions, right? And then Fraunhofer diffraction pattern can now be written in terms of this one, and it looks like intensity is now the absolute magnitude. It becomes a sinc square. So if you look at it, there is a central one and shifted downward, shifted upward. That means like this. Okay. So if you have an amplitude grading, then you have this diffraction pattern, right? So that's the main one. So it is shifted by these two factors. Okay. And so basically, if you have some kind of a amplitude grading, like this, and then you get And then along the x directions, you get peak. So center is a sinc function. And then on the top of it, we have our additional sinc functions. Additional sinc function, which is given by, which reflects the modulation frequency, f0. So remember that f0 was nothing but modulation frequency, okay? And then this is what we get for the amplitude grading. And then now we are going to think about some cases. So what we are trying to say is that diffraction efficiency of a grating is given by the fraction of the incident optical power that appears in the single diffraction order. So usually you say that, so eta 0, eta plus 1, eta minus 1. Okay, this is the 0th order and plus 1 order, minus 1 order. Remember that we have a light coming in. So there's this uniform intensity plane wave, and then it is distributed in this manner. Okay, so 0th order diffraction, 1st order diffraction, minus 1 order, minus 1st order diffractions. Okay, so if you look at it, diffraction efficiency is given by this amplitude intensity ratio. So here is the 0th order, 1st order, minus 1 order, and this is the plus 1 order. And then if you look at it, everything is sinc square, but the amplitude is 1 m square over 4 m square over 4. Okay, so that like this. So that the diffraction efficiency is given by 1. So it depends on the modulation depths. So if the modulation depths, the maximum of is 1. Okay, so that at best you can get is the 116, 116. And now we are going to talk about sinusoidal phase grading. And in this case, instead of intensity or amplitude, we have a phase. Phase is actually modulated by the spatial frequency f0. Okay, so it is very different from the amplitude grading. In terms of amplitude, is same 1, but it has a phase. Okay, and then by using the identity like this, okay, and then if you do the Fourier transform, exponential of this function becomes, if you do the Fourier transformation of exponential like this, becomes delta functions. And then what we end up with is that if you do the mathematics, then you get the Fourier transform becomes this one. And then here's the interesting factors, Bessel function, and then it is basically sinc function, okay? But if you look at it, it's summed over Q. It starts from the minus infinity to infinity. Note that amplitude grading, at best you can have 0, 1st order, minus 1, 0. But in the case of a phase grading, and you have a very different case. So rectangular is almost same, but you have a phase is modulated, and then you have a infinite peaks. Okay, is weighted by this JQ. And then eventually you get the intensity becomes JQ squared sinc square sinc square. Okay, so basically it's a sinc function, but it has a weight of this one, and then it has a many side peaks like this. Okay, so you have a q equal to +1, q equal to +2, q equal to +3, like this. So phase grading is spreading the incident wave more wide in the wider ranges, and then remember that it goes on infinitely. Q goes to infinity, and Q goes to minus infinity. Okay, so that it just spread out like this. And then its amplitude is given by it is decreasing. It is decreasing. So m over 2 goes like this. So remember that m was the modulation depth, so it should be around maximum is 1, so that half value, and then it goes like this. Okay. So thus far what we have done is the Fraunhofer examples. We start with the rectangular aperture, and then it becomes sinc function, and then we have a circle functions, and then becomes J1, and then intensity, and then we have amplitude grating, and we have three distinctive, and then distinctive diffraction patterns, and then we have a phase grating, and then we have a many peaks depending on the modulation depths. Okay, so this is what we have for the Fraunhofer. Fraunhofer case is nothing but, it's very simple, it's a Fourier transform. And then we are going to, in the next class, we are going to talk about Fresnel diffraction.